Hi, and this evening I'm sitting in front of one of our Sense It All potentiostats. I've actually got it set up to run a cyclic voltammetry, but I'm not going to use it because the Sense It All potentiostat can do cyclic voltammetry, and it will automatically send the data to a cloud system called Djuli. Now, Djuli is also more generic than just working with Sense It All, and in fact, what I'm going to do this evening is upload some data that was actually gathered on a third-party potentiostat, but then turned into a comma-separated variable file, or turned into a comma-separated variable file by yours truly. I'm just going to grab that file in for a second, just so you can see what I've done. I've cleaned it up a little bit, so I've just labeled one of the axes, the X current, and the Y essentially potential. And this is what I'm going to upload to Djuli now. So I'm just going to go into Tools. I'm going to add file from Explorer, so I can go here, open that, and up it comes. Now in the first instance, I won't see anything because I haven't given any instructions to Djuli. But what I'll now do is I will just turn off a few things and talk you through it. So I'll go into Properties. Whoops a daisy. This is a discrete experiment. So if I just choose discrete experiment and I close that, let's have a quick look at what we've got. So now I've basically got a view of that. So I'm not, in this video, I'm not discussing the origin of this cyclic voltammetry. I mean, it's fair to say this is the reduction of oxygen that I'm looking at, but I'm not necessarily discussing the kind of details of the electrochemical experiment. What I want to show you is the way I can process the data. So I've just clicked that again because I'm going to kind of leave some of the data in its raw format, but I'm going to go on to edit this data here, so I can see the raw data, and then I'll start editing the data. So just go into those tools really quickly, and the first thing I'm going to do is do some pre-processing. I'm going to crop the data, and I'm going to crop the data between 0 volts and minus 0.7 volts. So I just want to kind of see how that is looking. So I just have a quick look now. So I can see I've cropped the data, so I can see the kind of oxygen reduction here. The next thing I want to do is I just want to, just for convenience really, I want to just flip that around the y-axis. So let's just have a quick look at that. Yep, so now I've flipped it around the y-axis. You don't need to do that necessarily. Now what I want to do now is actually find that peak height. And I know that sometimes people are kind of worried about, not worried, but they think that the potential, the reference potential has to be very stable so that that peak is all the same position. But the way we can work with this kind of stuff, I'll just put 0.5 volts, 0.050 millivolts, sorry, 50 millivolts. Now this will open up a window. Let's just see what that window does. So I've put it in the wrong place. I should have put minus 0.5. So I'll just correct that now. So I shall put that at minus. Let's have a quick look just see what it did. Yeah. Okay, so I've put it in the sort of rightish place, if I can say, but I might just increase that window size a little bit. Now the reason being is I'm showing you this window is because what it means is that if you've got a peak height a peak that's part of your signal, it doesn't matter if the reference is shifting around a little bit, because we can open up one of these windows and you can see I can capture the peak height of that quite nicely. Now I want to show you that the way the Sense It All platform from Zimmer Peacock works is we can actually then go from raw signal to something like ppm of oxygen really quite simply. So what's happened at the moment now is I know what the peak height is because 1.43, I mean strictly speaking in the raw signal it was minus 1.43 nanoamps because it was a reduction, but I've just made it into the positive direction on the y-axis, just convenience. But now I have a peak height for that. But I actually want to turn that into ppm. So let's just go in and start turning that into ppm. So let's make my units ppm. And I'm just going to, now I really need to do a kind of proper calibration of this. But I'm going to literally, it sounds ridiculous, but I'm going to do some guessing of ppm. Now what I'm going to do here is I'm just going to turn 1 nanoamp. I'm just going to turn that 1 nanoamp. I'm just going to put a I'm just going to put quite a large number here, and then I'm just going to put 10 here, and I'll put 0 here. So let me just have a quick look what that's done. Yeah, so what that's done now then is basically taken my kind of I see that's 10 to the minus 4 there, so I need to increase this a little bit more. I'm just going to add 3 here and just see what that did. Right, okay, so I'll just add one more. I knew I was going to have another 0, but I just wanted to kind of make sure that I was doing that right. Let's have a quick look at that now. So what I'm basically doing is, rather than being left with peak height, I'm actually bringing it into ppm. Now I know that really the ppm in a, let's say this is an oxygen sensor for water. Now the oxygen concentration may actually be 6 ppm. I'm just making this up at the moment. So let me just have a quick play with some numbers and see what we can do with that. Let me just make that 5 for a second. 2.86, I went the wrong way, so let me make that 20. And I actually need to, I'm going in the wrong direction, my apologies. Let me just make that 2. Yeah, so by making that 2, then I brought that to about 7.15. So if I make that 2.5, that might be the last time I sort of mess with this now this evening. Yeah, 5.72. So I'm getting close to my 6. So I can tune that then to get to 6 ppm. So what I'm really demonstrating here is now I didn't use the sensor or potentiostat from ZP to gather this data. So I am showing you that though if we use the sensor or potentiostat, I would have gathered the data would have immediately gone to the cloud, and I could have actually processed it really quickly in the cloud. As it was, the data was gathered elsewhere. But what I'm demonstrating here is that we've got a very generic way of CV oxygen 2, a very quick way of actually processing cyclic voltammetry data. I could bring the raw signal up, I could crop it, I could rotate it, I could guess some calibration factors, and then actually reveal, give that, in this particular case, the oxygen signal in a cyclic voltammetry. Sorry, give the oxygen signal in ppm. So we can have one last look at that data, so just so you can see that, which I will do here. So we've got the raw signal, great, and then we've processed the data at least in 3 ways. We've cropped it, we've rotated it, we found the peak height, and we've turned the peak height into a concentration very quickly. And you can see that there's essentially no coding required here. And this means that we could actually then send this back to the app. And so rather than the person sort of having a cyclic voltammogram experience, they could actually have an oxygen signal experience. If you've got any questions regarding the sensor or technology stack from ZP or the Djuli in particular, which I've used this evening, please don't hesitate to reach out to us at ZP. Okay, thanks very much.